So just a little pre-note. I tried to do this video in slideshow mode, but my software keeps turning off whenever I go into slideshow mode. So we're gonna do this um, over here. So today we're gonna be looking at Cramer's rule, and we want to really derive it intuitively and geometrically. So let's recap what Cramer's rule is. It's an algorithm using the determinants of matrices and augmented matrices to be able to find solutions to systems, and this works for higher order matrices too. I'm not going to go too deep into it. I mean, we've done it a lot in this class. So a really important thing to really understand this derivation is defining matrices as a combination of vectors or a linear map, right? What does that really mean? When we say we want to define a matrix as a linear map, we're saying the x and y columns show you where I hat and j hat respectively get mapped to after you multiply by the matrix. A little confusing, but let's explain what that means. We actually have an example over here. So we can see I hat and j hat 1, 0, and 0, 1. We want to perform a 90-degree counterclockwise rotation with our matrix, right? So that'd map I hat to 0, 1 and j hat to negative 1, 0. And if we actually look at our x and y columns, we can put where I hat and j hat get mapped to, and whatever you multiply this matrix by, say it be another matrix or another vector, that's where your x and y coordinates going to get mapped to. So say my vector was 5, 0, so 5x and 0y, we'd get mapped to 0, 5, right? And I mean that is a 90-degree counterclockwise rotation. And that's what I mean by defining matrix as a linear map. Now let's define the determinant. So we can see the determinant as an area of a parallelogram. I mean, it doesn't really matter that it's the area of a parallelogram, but by looking at it as the area of a parallelogram, that's how we find it. What it actually is and how it really applies to us is that this determinant is a scaling factor. It takes the areas of other parallelograms. I'm saying parallelograms because the determinants of other matrices would be seen that way, but it takes those areas and it scales it by its own determinant. And there's even a way to look at a vector as a matrix, right? And this will play into what we're going to do later. And I mean, by looking at the determinant this way, it really helps you understand a lot of concepts in linear algebra, like why the product of all eigenvalues is our determinant, what the determinant of 0 means, how it relates to eigenvalues, eigenvectors, and why the determinant of a product of matrices is the product of determinants. I kind of gave that one away in the last slide, but let's continue. So let's interpret what a modified matrix is. I mean, for now, consider this vector. We want to put it in a matrix, right? So let's look at this blue matrix over here. We actually took the vector and we put it in the y column of the matrix. And in the other column, we just put I hat, right? If we look at the determinant of this matrix, it corresponds to our y coordinate, which is 2. It's pretty interesting, so let's take a deeper look at that. If we look over here to this picture, right, what this matrix really represents is a parallelogram made by the vectors 1, 0 and 1, 2, 1, 0 being I hat, right? To find the determinant over here without really computing it from the matrix, we can say that the area of a parallelogram is equal to base times height. Okay, what's the height of this vector? Well, it's just the y coordinate, or what's the height of this vector? Yeah, it's just the y coordinate of our vector. And what's the base? It's I hat, which is 1. So our formula is 1 multiplied by y. So it's equal to our y coordinate. And if you look over here, we also put the vector in the x column, and we also have the j hat unit vector in our y column. And we look over here, we can also figure out that, hey, the determinant is equal to 1, which is our x coordinate, right? This is going to be really useful in our derivation. So let's look at this system. Let's see how it actually gets solved through Cramer's rule, right? So we can draw our output vector 1, 3 as a parallelogram, right? But remember, we want to maintain continuity between what we saw as our old modified matrix, or our old parallelogram represented by xy, to our modified parallelogram represented by the vector 1, 3. Because if we look over here, what we're doing is we're taking a vector, we're modifying it by this matrix, and we get this vector back, right? So to really model this, we also have to modify I hat and j hat to figure out this determinant, right? Or this area of the parallelogram. But we said that if we look at matrices as a linear map, the x column and the y column, that's where I hat and j hat go. So we know where they go. We're able to find the determinant, right? And we're able to say that it is the respective coordinate of the respective parallelogram multiplied by the determinant of the matrix. Doing a little algebra, you can see that you get the same thing that Cramer's rule defines. Your modified matrix becomes either 1, 2 or 1, 4, right, in the x or the y column respectively, whenever you have the output vector 1, 3 in the x or the y column respectively. And finding those determinants and dividing them by the determinant of the original matrix is going to give you your x or y coordinate. This is a little tough to understand. I know I sat there for an hour looking at the same result, and it was pretty difficult to understand. But if we say the area of, say, the blue parallelogram is y, it gets multiplied by this matrix. So what happens is this area gets scaled by the determinant of a. Then what we can say is this new determinant divided by the old determinant is equal to our y coordinate. And that's what Cramer's rule is just stating. It's definitely a hard derivation to really get into your head because sometimes linear algebra isn't so intuitive, right? And especially if you're trying to look at it from, say, a higher order, even a 3 by 3 square matrix is going to give you difficulty when trying to analyze it, right? So, I mean, don't be afraid to watch this video again. But I had a lot of fun doing this, and I think it was a really good experience, and I definitely do it again. Thank you for the experience, and these are my sources.